Hi, today we're going to be taking a look at the natural log function and integration. Now yesterday we discussed that the derivative of natural log was 1 over u. And so therefore it stands to reason that if we take the antiderivative of 1 over u, we're going to get the natural log. Now be careful, there is a kind of a condition here. This only works if the power on bottom is 1. If the power on bottom is 1. It doesn't work for something like 1 over x squared dx, because I could rewrite this as x to the negative 2 dx, which gives me negative 1 over x plus c1. The problem occurs if we try to do 1 over x. If I try to integrate this, I would get x to the 0 over 0, and we can't have that. So we have a new rule. That's our it becomes natural log. So if we take a look at this problem right here, if I want to integrate 2 over x, if I use my rule, I do have a constant, so I can take out the 2, and I get 1 over x dx. Now when I integrate this, the 2 stays, but our new rule says the antiderivative of 1 over x is the natural log of x. Now we like to put this in absolute value because we want to guarantee that it stays positive always, plus c, but don't forget your plus c1. Now you could write it as this, the natural log of x squared plus c1 as well, and you don't need the absolute value because anything squared is already positive. Most books are acceptable with this. Alright, now, if we take a look at the second example down here, it's the same problem as you noticed, but this time we have a domain on it. So this is our definite integral. So if I integrate it, we already know what that becomes. We're going to go from 1 to e, and this is just 2 natural log of x. Right? And if I do my FTC, f of e minus f of 1, phi, and I guess we have f of 0, fo. Alright, funny stuff, I know. So if I simplify this, plugging them in, I get 2 natural log of e minus 2 natural log of 1. Now you can leave it like this, but it simplifies. We all know the natural log of 1 is just 0. And over here, we can get 2, and the natural log of e is just 1. So I just get the number 2 here. Very easy to do. We can also apply U-substitution. Now remember when I said the power on bottom must be 1, and that's what I have down here. If I think of this entire denominator as just a single quantity with the power of 1, I can apply my U-substitution. We'll let u equal 2x minus 1. Our du is 2 dx, and dx equals du over 2. And I rewrite out my problem in terms of u. So I get 1 over u, I over u, like a good breakup text, I over u, and I get du over 2. And I can factor out the 1/2, we get 1/2, and I get the antiderivative of 1 over u du. So our final answer, 1/2. Remember, this is the natural log of u plus c1. And now I just got to replace my u, so I get 1/2 natural log, u was 2x minus 1 plus c1. And there's our answer. Don't forget the absolute values on these. Trying the next one, number 4 here, is a little bit tougher to find the u. So another, to find u. Cool. Alright, so anyways, what we're going to do here is I'm going to look for the derivative. Well, I know if I take the derivative of x cubed plus x, I'm going to get 3x squared plus 1. So there's u. u is going to be x cubed plus x. Give me du as 3x squared plus 1. Don't forget your differential, dx. Solving for dx, we're going to get du over 3x squared plus 1. And I can just substitute this back in. And I'm going to get 3x squared plus 1 over u. And times, replace the dx with du over 3x squared plus 1. And you notice those cancel out. And what are we left with? 1 over u du. And you go to your answer. This becomes the natural log of u plus c1. And I got to replace my u now. Got to replace u. X cubed plus x plus c1. I am so funny. Alright, there we go, and there's our antiderivative. Alright, now the next one a little bit tougher. We don't know the antiderivative natural log yet. We have to use what's called integration by parts for that. But we are in luck. This is a traditional U substitution. U is on the inside function. So U, in this case, is just 1 plus the natural log of x, giving me du. Be careful, I get 1 over x dx. And dx therefore equals, be careful, it's not going to be du over x like we used to. We get x du. And that's what I wanted. So now when we replace, we're going to go get u cubed over x times x du. Now notice I did not replace my domain yet. Okay, we're going to talk about that in a moment. But notice my x's cancel, and I'm going to be left with u cubed, my favorite mathematical pickup line. Now, at this moment, what we're going to do is change our domain. This is all in terms of x. X, 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 x. Now we're in terms of u. And that's what we want. So now we can replace our domain. I know when x equals 1, u equals, be careful, it's 1 plus the natural log of 1. And we know the natural log of 1 is 0, so this is just 1. When x is e, we get u equals 1 plus the natural log of e. Well, the natural log of e is 1, so we get 2. So we're going from 1 to 2. Very easy to do, and now we can integrate it. Again, you can pause it any time you want if you need to slow down. I'm going to integrate from 1 to 2, and we're going to do a fundamental theorem, f of 2 minus f of 1. And this becomes 2 to the 4th is 16 over 4 minus 1/4. Notice I didn't write that as 4 because I got to subtract anyways, and I get 15 over 4. So at this point, if you'd like, pause and then try the last one here, and you can try that one real quickly, okay? See how you do. I'll wait for you. And we're back. Good. Let's see how you did. Hopefully you chose the natural log of x as your u, because that's my inside. So your du becomes 1 over x dx, and dx becomes x du. And I replace everything. We're going to get the antiderivative of u to the 4th over x times x du. And again, notice I haven't replaced my domain yet. I'm going to wait for that. Wait until my x's cancel, and I'm going to get u to the 4th du. Now I'm going to look at my domain. See, now I look at my domain. When x equals e, we know u equals the natural log of e, which is 1. So we go from 1. When x equals e squared, u equals the natural log of e squared. Well, that's just 2 because those cancel. So we're going from 1 to 2 here. And when you integrate it, you should get u to the 5th over 5 from 1 to 2. Plugging in, we're going to get 32 over 5 minus 1 over 5, and we should wind up with 31/5. And there's our answer right there. Very, very easy to do. All right, now let's take a look at a hard one here, okay? This is a tough one right here, this next one. Okay, so now, for this one, U-substitution won't work. So we have a rule. This goes back to our rational functions. What does this function look like in the end? And when we take the limit as x goes to infinity, we're going to look at the horizontal asymptote. And that basically gives me what the shape of the graph looks like. Kind of an example, if I did the limit as x goes to infinity of 3x plus 2 over x minus 1, we get 3. That's my horizontal asymptote. So what that means, if I go off to infinity, big numbers, this is all just going to be the line y equals 3. That's basically what a horizontal asymptote does. Tells me what the shape looks like in the very end. Well, this one was a little bit different. When we did rational functions, we would have to do some polynomial division. And that's what we're going to do here. So we have a rule. If the top power is bigger than the bottom one, we call that big on top. Or as I like to call it, the bot. Doing the bot. The bot. Anytime you have this, you want to use division. So we're going to use polynomial long division. Now, some of you are thinking like, Mr. Wernow, can we use synthetic division? You can, and synthetic division will work on something like this, but synthetic division only works best if the denominator is a linear factor. In other words, the power down there is 1. Otherwise, long division is always the best, because you will have some times when this is like x squared or x cubed, and synthetic division is a lot harder to do with those. So I'm going to divide this x plus 2 into this x squared, put a 0x there, minus 5. And I just divide. X goes to x squared, x squared 1 time, so I need another x. So this goes x squared plus 2x. Don't forget, we're going to subtract, so we get negative 2x, bring down the minus 5. And then I got to multiply x by negative 2. I get negative 2x minus 4, change the signs, I get not that one, that stays minus, and I get minus 1. And you may remember how to write this. We'll go minus 1 over x plus 2. So in other words, this integral is the same as if I wrote x minus 2 minus 1 over x plus 2. It's my slant asymptote from Algebra 2 and Pre-Cal. Because the slant asymptote is really what does the function look like in the end. So this function and this function are the same. They look exactly the same. Now, taking the antiderivative, this one's not so bad. Now, I'm not going to worry about the domains here. You'll have one like that in your homework. We get x squared over 2 minus 2x. But over here is our tricky one. This is our new one. The bottom power is 1. This is our natural log rule. So we know u equals x plus 2. My du equals dx. That's nice because not much to do for this one now. We go minus, remember this is 1 over u, and this becomes the natural log of u, but we know u is x plus 2, so I can just put that back in. Don't forget your constant, plus c1. Alright, before we go, I'm going to take a look at some trig ones here, okay? Actually, if you want to, I'll put these on another video, keep this a little bit shorter, okay? So what I would like you to do, go to part 2, and we'll take a look at how we can do the trigs, okay? Alright, and we'll do some proofs on them as well. Thank you.